In this section, we are going to study the variation of graphs and how we can analyze the graph. We will explain how the graph is changing and what is its gradient. To understand this objective, we are going to take example 2 from page 204. A dog is running in a straight line away from its owner. Part of the distance, time graph describing the motion, is shown. So the dog is running away from its owner, and they are observing the distance covered with respect to the time as shown on the graph. Thus, the y-axis represents the distance from the owner in meters, where the scale for each unit is equivalent to 10 meters, while the x-axis represents the time in seconds, where the scale to each unit is equivalent to 10 seconds. In Part A, it is required to describe how the dog's speed varies. According to the graph, we can see how the speed of the dog is changing. So if we look at the graph, we can see that there is specific points. And if we connect these points, such as A and B, we will have a horizontal line. According to the line, we can notice that in the first 10 seconds, the dog is still 10 meters away from its owner. But if we connect the points B, C, and D, we will get a curve, not a straight line. While if we connect the points D and E, we will get a straight line. Remember that the gradient of a distance time graph gives the speed. So for the first part of the graph, from point A to point B, we got a horizontal line. The straight line means that the gradient is equal to 0. The gradient is 0, so the speed is 0. Therefore, the dog is in a stationary position for the first 10 seconds, which means that the dog for the first 10 seconds is still not moving. It is 10 meters away from its owner. Now, from point B to point D, if we draw a tangent, it will increase its gradient. Notice that if we draw a tangent, it will be like this. Then it will increase in this way. So the gradient is increasing. Therefore, from B to D, the gradient is gradually increasing. Since the rise is increasing, so the speed is gradually increasing. For the next 30 seconds, the dog runs with increasing speed, which means between the time 10 seconds to the time 40 seconds, the speed is gradually increasing. It started out as stationary, and then it gradually increased, while from point D to point E, a straight line is drawn, so the gradient here is constant. The rise and the run at all points will be the same, so the gradient is constant and its value will be 30 divided by 20. The rise is between 30 to 60, so it is 60 minus 30, which is 30. The run, according to the time, is 20. So if we divide the rise by the run, which is 30 divided by 20, we get 1.5 meters per second, which is constant throughout the points D to E. So the gradient is constant and is equal to 30 divided by 20, which is 1.5. So the dog is running at a constant speed of 1.5 meters per second. Therefore, if the line is horizontal, then the gradient is equal to 0. This means that there is no movement and no speed. The increasing curve means that the gradient is increasing and the speed is increasing as well. The new straight line means constant gradient and thus a constant speed. In part B, we have to estimate the dog's speed after 30 seconds. After 30 seconds means at time equals 30 seconds. We have to calculate the speed at point C, so we have to find the rise and the run. We will draw a right triangle. The run is 50 minus 30, which is 20 seconds. For the rise, we have to see the distance horizontally, which is between 35 and 20, so it is equal to 15 meters. And because the straight line is going upward, so the rise is positive. So to find the gradient or the speed, we divide the rise by the run, which is 15 divided by 20 equals 0.75 meters per second. So the speed of the dog is approximately 0.5 meters per second. Throughout this example, we have learned how to study the variation of the graph, where the graph had a zero gradient, increasing gradient, and a constant gradient. We also learned how to find the gradient at a particular point, as in this example, which represents the speed at a distance-time graph.